In this video, we are going to investigate several more common types of problems that we will encounter involving derivatives. So the first of which, the graph of a function y equals f of x is given here. And what we would like to do is use this graph to sketch the graph of its derivative. And the key observation that's going to allow us to do this fairly efficiently is to note that the derivative of a function at a point is the slope of the tangent line to the graph of that function at a point. It's one of the big geometric interpretations we have of the derivative, slope of a tangent line. So looking at the graph that we are given, it's just a line. If I pick any point that I want on this line, I'm just randomly picking a point. If I draw the tangent line, note that it's simply going to be the graph of the function f itself. So at any point on a line, the tangent line is just the line. So we think, okay, so what is the slope of this line? If we look at 2 points that we can see on the line, we have the point 0, comma, minus 1, and it appears we have the point 1, 1. So the slope would be rise over run. 1 minus a minus 1 over 1 minus 0 is 2 over 1, or 2. So at any point on this line, the tangent line is the line itself, and it has slope 2. So what that's telling us, because every point has a tangent line with the same exact slope, f prime of x is simply the number 2. So if we wanted to sketch that, f prime of x is going to be the horizontal line given by y equals 2. So in this case, we were lucky enough that we could actually even write down explicitly what that derivative is. We will see that this is not always the case. So a very similar example, we're given the function f and we'd like to sketch its derivative. So this one's going to be a bit more thought-provoking, but what we're going to do is develop kind of a general procedure that one could apply. So in order to sketch the derivative, we're going to think about what happens at a few key points. And the key interpretation of the derivative was that it is the slope of a tangent line at a point. So what we are going to do is think about where will the derivative be 0, and the derivative will be 0 when the tangent line is horizontal. Because remember, a horizontal line has 0 slope. So looking at the graph of our function, at 0, we see that if we draw the tangent line there, it's going to be a line with slope 0. So what that's telling me is that f prime of 0, because it corresponds to an input of 0, the tangent line has slope 0. So when we graph f prime, it's going to pass through the point 0, 0. Likewise, it looks like at the point 2, if we draw the tangent line, it is also horizontal. The slope of that line is 0. So f prime of 2 equals 0. So when we draw our derivative, it's going to have a value 0 at 2. And those correspond to the only 2 points on the graph with a horizontal tangent line. So what we need to do is just think simply about what happens in between. In between these zeros, the function is going to be, in this case, the derivative function, is going to be positive or negative. And we need to think about whether it's going to be positive or negative based upon looking at some slopes of tangent lines. So we know the value at 0 and 2 is 0, and we're going to think about what happens at a few key values in between. So if I look anywhere between 0 and 2, and I look at a point on our graph, if I draw the tangent line at this point, that is a line with negative slope. When we move to the right, it goes downward. So the slope of this line is negative. So in between 0 and 2, the value of the derivative is going to be negative. That is, the tangent lines to the function f have a negative slope. If I look to the right of 2, and I pick a point, wherever I draw that tangent line, we see that it's a tangent line that goes upward as you move to the right. So the slope is positive. So the positive slope of a tangent line tells us the value of the derivative is going to be positive. Likewise, if I pick a point to the left, of 0, the tangent line is also going to have a positive slope. So the value of the derivative when we're left of 0 is positive. So let's put this information together and see if we can sketch f prime. And I'm going to sketch it here in blue. So if I look between 0 and 2, at 0, the value of the derivative is 0. And then it looks like it starts off where the slope of the tangent line is getting larger and negative. And then at a certain point here, it looks like the value of that slope of the tangent line is approaching back to 0. So in between 0 and 2, it looks roughly as though the value of the derivative should be something like this. So the slope of the tangent line starts off being at 0. It gets more negative, and then it gets closer to 2 again, closer to 0 again. If we look to the right of 2, you're starting off with kind of a small value for the slope of the tangent line, but the further right you go, the larger that slope is going to become. So it's something that's increasing. Similarly to the left of 0. Close to 0, it looks like you have a relatively small positive slope, but the further over here you get to the left, it looks like a larger and larger positive slope. So roughly speaking, this blue function represents the derivative. Now, note this is really the best we can do in the sense that we can't be extremely accurate, but what we can do is definitely indicate where the value of the derivative will be 0. That corresponds to the tangent lines being horizontal. And then we can look in between where those tangent lines are horizontal and think, will the derivative be negative or positive? And that's going to give us kind of this basic shape that the derivative function will take on. I would like to now further investigate the derivative from this graphical perspective. And kind of a key property that's going to help us out is that if a function is differentiable at a point, it's also going to be continuous there. And what's more important here is that this is telling us that if a function is not continuous at a point, then it is not going to be differentiable. And this leads us to, I'm going to say, 3 main ways that a function will fail to be differentiable at a point. So a function that fails to be differentiable at a point will be in 3 main ways. It will be something where, 1, the function f is not continuous. So if you have a point on the graph, in this case, the function value is not equal to the limit value, so it's not continuous, it will not be differentiable. The second way we have is when the graph of the function contains a sharp corner, or we might think of it as being a cusp. The reason it would fail to be differentiable here is that there's not a tangent line to the curve. As you approach from the left, you have, it looks like, positive tangent lines, or positive slopes. From the right, negative slopes. The third way a graph will fail to be differentiable is when the tangent line itself is vertical. So if you have a vertical tangent line, its slope is undefined, but that is the derivative. So the derivative itself would be undefined. So let's put these 3 main ideas to use. So fails to be differentiable because a function is not continuous, contains a sharp corner or cusp, or a vertical tangent line. So we have the graph of a function given, and we would like to determine at which numbers the function f will not be differentiable. Looking at this graph, I immediately see 2 points jumping out at me. There's this sharp corner or cusp at 3, and the function fails to be continuous at 0. So there are 2 values where this function is not differentiable. So the first is x equals 0, because f is not continuous at x equals 0. The second would be x equals 3. And the reason it would not be differentiable at x equals 3 is because the graph at 3 is a cusp. Because the graph has a cusp, or we might call it a corner, at x equals 3. So very similar here. We're given the graph of a function. We would like to know where it fails to be differentiable. And I'm seeing in this problem 4 points that are jumping out at me. We see kind of this behavior at -2, where the function has what looks to be a vertical asymptote, which means it's not going to be continuous there, even though it's defined. At -1, we have that sharp corner or cusp. At 2, the function is not defined and hence not continuous. Likewise, it looks also like maybe it would have a sharp corner or cusp if that value was there. And the other point I see is at 0, that if I draw in the tangent line to the graph, it's going to be vertical. So this function is going to fail to be differentiable at 4 points. At x equals plus or minus 2, it fails to be differentiable because f is not continuous at x equals plus or minus 2. At x equals -1, it fails to be differentiable because the graph of f has a cusp at x equals -1. And lastly, x equals 0, because the tangent line, and I use TL for tangent line, to the graph of f is vertical at x equals 0. And the reminder is that the value of the derivative is the slope of the tangent line. The slope of a vertical line is undefined, which means the derivative is undefined at that point.